equation.
Yeah, thank you. Okay, first, of course, thank you that I get to present my work here that I did together with my advisor, Marius. Okay, what am I going to talk about? So I want to tell you about all 4x4 solutions, so the quantum Young-Baxter equation. So I'll have to remind you what's the Young-Baxter equation. It's this. Then I have to tell you how we solved it. Then I have to show you our solutions, and then I'm gonna switch gears a little bit and talk a little bit about relations between R matrices and lax operators and how these relations break, leading to the modified Young-Baxter equation. Okay, so we said this is the Young-Baxter equation. This is also it, but as an equation. And R, we know, is some operator from a tensor product of vector spaces to themselves. For us, this vector space is C2, therefore 4x4 solutions. R also depends on some spectral parameters, which are just some complex numbers, but importantly, they're non-physical, so we want our equations to hold for any value of them. The first thing you could try when you want to solve this is put all these parameters to be equal, which we would call a constant solution. Luckily for us, these solutions have already been classified in 1992. Luckily, because we're actually not that interested in constant solutions, but they're very practical because we can expand around them in the spectral parameters. So in short, what we more or less did was expand around these constant solutions, plug it in, solve order by order. Very simply said. The most common and best studied solutions are called regular solutions, and they're defined by setting this constant R0 in the beginning to be the permutation matrix. In the 4x4 setting, these solutions have already been classified by Marius and Luke, which are here somewhere. Of course, the regular solutions are also probably your favorite solutions, like XXX, XXZ. They correspond to regular solutions. Still, we wanted to complete this classification by now also saying, okay, what happens if this is something else than the permutation matrix? What is if this is something of these constant solutions? And actually, we were inspired because about a year ago, there was already like an algorithmic approach by this group where they solved the Young-Baxter equation with some algorithm, and they found some non-regular difference form solutions. So we said, let's go, let's do them all, let's find them all. So how did we do it? As I said, we just had some expansion and we plugged it in. This is a tiny bit more detail. So as you might know, if you ever try to solve Young-Baxter equations, it can get difficult, so you have to be a little bit clever. And our two clever moves that we did was do a change of variables from just uv to u minus v and u plus v. Then you can expand in just one variable instead of two. That already makes your life easier. And then instead of solving the whole Young-Baxter, you just solve this set of necessary conditions, which you get by setting two of your spectral parameters to be equal, or setting u minus to be 0. Of course, if you solve this now, you'll have to in the end check that the Young-Baxter equation is actually satisfied. But yeah, so you take your expansion, you plug it into your conditions, and you solve order by order. This is more or less what we did. And which kind of models did we find? Well, we found some full rank solutions, some diagonal ones, some of XY type, like here with poly matrices. We also found some difference form solution. That means here with just depending on the difference of spectral parameters. Otherwise, all of these Fs are just some general function. We also have some 8-vertex type solutions and some lower rank solutions. So our R matrices are not necessarily invertible. So you'll have here rank 3, also rank 2 and even rank 1 solutions. Okay, you can in theory form charges with them. From the diagonal, you'll of course find diagonal charges. Here you might find some Hermitian charges. So far we have, but in quite generically, the charges you'd find would be long range. Okay, are there any very short questions about this classification? Otherwise, I'll switch gears a little bit and talk about relations between R matrices and lax operators. Okay, so this is just to remind you about the RLL, or fundamental commutation relation here, and why we care so much about it. So we care about it because if we have it, we can construct from it a tower of commuting charges, which is what we use to understand integrability. So at an integrability conference, we care very much about this relation. And if we look at it, we note, or we already know, that this is very similar to the Young-Baxter equation. And also this lax operator is defined very similar to the R matrix. So what we wanted to do was we wanted to somehow rigorously denote these relations, these similarities. And we did this in these, this is 4 statements covered in how we denoted them in our paper, Proposition 3 and Theorem 1. Proposition 3 tells us that if we have a regular lax operator that satisfies this fundamental commutation relation, then the corresponding R matrix has to be regular as well. So you would have this regular, then you know this has to be regular as well. We proved this by simply expanding L, expanding R, plugging it in, and then doing some massages using permutation operators. So now you could ask, okay, this is nice, we know this now, that's nice that we proved it. You could ask, could you do this with non-regular as well? Could you basically ask, let L be a non-regular lax operator that satisfies this, does R also has to be non-regular? And you could assume, okay, maybe because we use the permutation operators a lot, maybe not. And actually, we have, you can even find counterexamples to such a claim. That means you could say, you could have here a non-regular L matrix and find a regular R matrix that satisfies this, which is weird and unexpected, but that's kind of the headline of non-regular R matrices. The next 3 statements that we found are kind of all baked into this Theorem 1, which says that if you have an R matrix that satisfies the RLL relation and L is regular, then R will also satisfy the Young-Baxter equation. Furthermore, it will also satisfy braiding unitarity, and there is a direct correspondence between those R satisfying the Young-Baxter and the lax operators. So for obvious reasons, I'm not going to prove all of these things now. But again, you will have to do a lot of massages using permutation matrices, which you, again, could not do if you had non-regular lax operators. So if you tried to make a statement like this for non-regular laxes, it would look something like, your try would look something like this. Take a non-regular lax operator and try to solve your RLL relation for some unknown R. What you might find is an R matrix that doesn't solve the Young-Baxter equation. Perfect. Instead, it might satisfy something like this, which we called the modified Young-Baxter equation, with this M just being some big matrix depending on all spectral parameters, and which we had not found up until now that it satisfies any cute relation or equation. it's also fixed. Like for a given r tilde, m would be fixed. So this brings us to my outlook and takeaway. So the takeaway is that all the existing formalism works like a charm for regular models. We proved a lot of things that we have had a gut feeling would be true anyways, but we also showed that once things are not regular, all of this gut feeling kind of breaks down and proofs don't work anymore and relations don't work anymore. Because of that, it would be very interesting to find some kind of formalism that does work in a regular setting. It would be interesting, maybe we could find models that are in blockwise regular, maybe we could find local charges there. If not, it would be also interesting to look more at these models that are inherently long range and see if we could find non-trivial models there. And then of course, we could always come back to this modified Young-Baxter and see if we could reformulate it in a more appealing way. Okay, that's it for me. Thank you for listening.
Thank you very much. Are there any questions? Yeah, Kolja? Oh, okay. No one listens to me, obviously.
Yeah. Thanks for the talk. I was wondering, so this modified Young-Baxter equation, if I take a classical limit, is it like the modified classical Young-Baxter equation that defines,
No, so far we were not able to map this because there has been we have not been able to map this to the modified classical. There has been other questions also in this direction, could you find this to be related to the trapezoid tetrahedron equation? Could you map this somehow to a dynamical or twisted? No. So far, no.
Hi.
How many of out of this 4x4 solution you found would build up some unitary evolution?
So far, these two build up symmetric charges, Hamiltonians. None of the rest were either Hermitian, symmetric, antisymmetric, nothing of this sort.
I have a question about the solution of Young-Baxter. So your solution is based on the statement that you can tailor expand your solution around the constant one, right?
Yeah.
But why is this true for any solution to Young-Baxter?
You're asking if this is true for any solution?
Yes.
I mean, as long as it's analytic and differentiable, maybe you could come up with something really weird.
Okay.
Anything else? Yeah? So it is.
So this is not a question, but more a comment to the previous comment. I mean, generally, you can assume that there is some region in the complex plane where the solution is analytic. And then when you can tailor expand there, and generally you can always resum the solution back up to some solution which may in general be complicated, like some square root structure or something like this. But I mean, this assumption of regularity is not really much of a restriction at all.
Okay, thank you. Was it the ones that is it this one that you mean, or is it a different one?
Oh,
So no, they do the regular solutions. We focus here on the non-regular ones. So all their solutions reduce to the permutation operator, but at higher rank. So these are different.
okay. Maybe we'll stop here and we can ask more later if you have questions. Thank you very much, Vera. Okay, so our next speaker is Anders Wallberg. He's going to be talking about Orientifolds, crosscaps, and integrability in n=4 super Young-Mills theory.
Thank you. So I would like to thank the organizers for giving me this chance to talk. Before I go into this complicated business of Orientifolds, I thought maybe first I would talk about a slightly simpler case, which luckily Charlotte already covered earlier today. So this is this duality between probe D branes in the ADS5 x S5 geometry. On one hand, adding defects to n=4 super Young-Mills on the dual side, and the so-called matrix product state on the PSU 2,2/4 spin chain, or in general some other boundary state on the spin chain. And what has been found previously is that all these three sides are related very nicely. You can map observables in one to observables in the other. And this has been explored over the last 10 to 15 years, and we found very good agreement on all three sides. Now, what we wanted to do was extend this study to another set of objects in string theory, which is the Orientifolds. So these are much less studied than D branes in general. They share some of the same features. They carry tension. They are extended objects in various dimensions. But they're also different in many ways. They're non-dynamical. The tension can often be negative. And they're only really understood in perturbative string theory. So it'd be nice to have some setup like ADS5 x S5, where you can actually go away from the perturbative regime of string theory. But what is the dual of these? Well, one hint comes from the fact that Orientifolds can also be interpreted as crosscaps on the world sheet. And that word crosscap came up in a different setup, which is that of n=4 super Young-Mills on projective space. So in general, if you take a CFT and place it on projective space, that's known as a crosscap CFT. And it shares many of the same features as a defect CFT. You break some conformal symmetry, you get new observables, you get cross ratios appearing already in the two-point function, and so on. And then what would be the natural candidate for a spin chain dual of this? Well, that would be that of the crosscap state. So whereas the matrix product state I had on the previous slide sort of entangled nearby sides on the spin chain, this crosscap state entangles sides on opposite ends of the spin chain. So it's sort of long range entangled. But what we wanted to figure out is, are all these three things actually related, or is it somehow, they're all called crosscap, but they actually have nothing to do with each other? And in particular, that requires some specific setup for this n=4 theory. That's a bit non-trivial. So for this talk, I'll focus mostly on the n=4 side, but I'll comment on the two others as we go along. So what is this theory on the projective space? Well, the idea is you identify points that differ by a conformal inversion. So here we have some point x, and we identified with the point x prime that differs by a conformal inversion. And so if you have some operator located at x, you should identify it with an operator located at x prime, and this operator will not be the same operator, but modified ever so slightly in a way I'll come back to in a second. And this breaks conformal invariance, so now you only have an SO5 symmetry. Note here that maybe some of my time-like directions are slightly different from what you're used to seeing because we're working in a Euclidean setup here. Now it turns out that if you want this to be half BPS, you also need to break R symmetry. Again, this is similar to what people know from the defect cases, but maybe more non-trivially is that to have a nice integrability interpretation, it turns out that we need to also break gauge symmetry from SUN down to SON via a certain charge conjugation. And what that tells us concretely is that if you take some scalar Z, we should identify this sort of Z prime will not be Z itself. There will be some conformal factor, 1 over x squared. There will be a bar, which comes from this breakdown of R symmetry. And there will be a transposition, which comes from this breakdown of gauge symmetry. Now that looks a little bit puzzling. I'll come back to why this is natural in a second. But let's first see what some of the consequences of this are. So first of all, propagators in this crosscap theory are slightly modified. So if you work in a free theory, you can normally derive propagators just as Wick contractions. But here it's slightly different because you now also need to consider Wick contractions not just between your two operators, but also between your operator and the mirror image of your operator, this O prime. And because the mirror image has this transposition, you get these sort of twisted propagators that twist as they go along. Okay? Now, if you then try to compute one-point functions in the theory at tree level, they just come from Wick contraction. And you find that they are actually order 1 in n. They don't scale with n. And if you work at tree level and to leading order, they're actually very easy to compute. It turns out there's one unique diagram that contributes. And the way it works is that you arrange your operators around in a circle like this, corresponding to their color structure. And you then Wick contract operators on opposite ends of the circle. And you can check that this is the only diagram that contributes at leading order. So for example, here I have 6 operators, and you'll find that I have 3. So here the colors each correspond to one loop in the diagram in the n factors. So here we have 3 loops, and that's the leading contribution. Okay? Now that diagram should look kind of familiar from my previous slide. This is how you see in n equals 4 that you get the crosscap state on the spin chain, right? So here we were identifying sites on operators on opposite ends of this circle I drew, and in the crosscap state we should do exactly the same. We should identify sites on opposite ends of the spin chain. And this setup turns out to be integrable. So if you want to compute these one-point functions, it can be mapped precisely to the overlap between a beta state and your crosscap state on the spin chain. Very similar to what Charlotte was showing for this defect case, where here instead of the crosscap state, we had this so-called boundary state. Now, for bosonic spin chain, it turns out that this overlap is given just in terms of this superdeterminant. So maybe you remember Shuta's talk from 2 days ago. He had all these complicated factors in front of the superdeterminant. Turns out that they are not there for bosonic crosscap. But we're not so lucky that they're never there. If you go to a super spin chain, they do appear, and they're actually even more complicated. So for the experts in the audience, they're not just ratio of Q functions. They are some more complicated object. But we can still try to write down a formula for them in general. Okay? So this was the spin chain side. What's happening on the string theory side? Well, there the object in question is a probe O1 brane. And turns out that in this setup, this probe O1 brane is orthogonal to our stack of D3s that make up the n equals 4 theory. And we can even perform some naive matching in the BMN limit, although there's much more to be said about the Orientifold side of this to understand it better. And also here, this mysterious transposition we had, this charge conjugation that was necessary, has a natural origin, which is that Orientifolds are known to reverse churn pattern factors. So that comes from the fact that they reverse orientation. So they also flip around which where your string starts, which deep range starts on and which it ends on. And that's the precise analog of this transposition we had earlier. So it's in fact quite natural. And that brings me to some further work we're doing. So these crosscap CFTs can also be defined with fixed points. So the map I showed you earlier, this conformal inversion, had no fixed point, but we can allow for fixed point, and this new crosscap defect mixed theory has features both of crosscap CFTs and defect CFTs. They appear to be new, haven't been studied before, so we have proposed what their structure is in general, and also been exploring it for the ON model in particular as a simple example. And then one reason why we're interested in this is that if you now do this setup in n=4, it should correspond to orientifolds of various dimension in various orientations, all of which can now have a natural origin in n=4 Super-Young Mills, and we hope to also explore this and have a whole host of theories we can study. Thank you.
Any questions? Yeah, Kolja?
So in this crosscap, can you have like composite operator asymptotically sitting at the origin? Would it define some kind of anomalous dimension then?
Sorry, in what? You mean in...
Like send some operators to the origin, so they're like all in, and then another one is mapped to infinity?
You mean adding on top of the crosscap?
As I understood, you insert your operators one-point function, they just in some arbitrary location.
Mm-hmm.
But
yeah, so you can add.
But zero is special, right? Because map.
Yeah, so it's mapped to infinity under this map, but otherwise you can add operators at any point you'd like.
Mm.
So the crosscap state you discussed, does it break supersymmetry?
Sorry?
How much supersymmetry does this state break?
It's half BPS.
Half BPS. And the chiral operators, do they have one-point functions or they are protected?
I couldn't tell you from the top of my head. I think in general, yeah. I think in general in this setup, I think you should expect all. Okay. We can talk about it afterwards. I'm not sure on the top of my head.
Yeah, let's discuss later.
Is there a reason why it's SON as opposed to SPN, gauge theory?
No, you can also do SPN. This was just to make it slightly easier. But you will have both. And on the, it doesn't make a huge difference here. So there's still a very natural interpretation in terms of the spin chain. But in the string theory, this is then also in string theory, we know that there are different types of orientifolds with different signs of the tension, and we can allow for both in general.
Okay, thanks.
Any more questions? If not, let's thank our speaker again. And our next speaker is Levine. He's going to speak about convexity of scaling dimensions over conformal manifolds.
Thank you very much. So thanks a lot to the organizers for this very nice conference and for the chance to tell you about this work. So let me begin by showing you this plot, which some of you in the room are responsible for. So, we have these beautiful plots from integrability. So we should look at them and try and scrutinize them and see what we can learn from them. And one thing I want to point out is that these single trace scaling dimensions in plane n equals 4 appear to be monotonic functions of Toff coupling, empirically. And more than that, if you plot them as functions of lambda instead of square root lambda, they look concave. And that's actually a more fundamental property, because concavity implies monotonicity for functions that blow up like the positive power of lambda for large lambda. Okay? So it's kind of intriguing, and you can ask some integrability experts, why does this happen? I asked some of you actually over the last year, and I didn't really get satisfactory answers. So that's kind of what drove me into this project. And actually, you can see that this property persists at least for like lightest operator at finite n. So this is the data we have from the bootstrap by Chester, Dempsey, and Pufu. And they sort of believe that these upper bounds are saturated because here they fed into the bootstrap these integrated correlator constraints. So you can see that each of these curves is the upper bound on the lightest unprotected scalar, where n goes from 2 to 11. In each case, I've drawn this black wall, which is the self-estial point. So the two sides of the wall are like reflections of each other. You can just look to the left of the walls, and you see that each curve looks concave on the left of the walls. Okay, so it's kind of tantalizing. So I'd really like to understand why that happens in n equals 4, but actually for some technical reasons, which I can mention later, odd space-time dimension is much simpler. So in this first part of the project, I'm thinking about similar question, but in odd space-time dimension. And so I'm thinking about unitary CFTs in odd space-time dimension with exactly marginal couplings. I'm thinking here about conformal manifolds. And I have additional technical assumption that there's no mixing in this low-lying part of the spectrum between operators with even integer gaps. That doesn't really play a role. And the result is that for any choice of quantum numbers, delta, the dimension of the lightest unprotected scalar, is a concave function over the conformal manifold with respect to the Zamolodchikov metric. So that just means that its covariant Hessian matrix is negative semi-definite. And more generally, the sum of the lightest n scalars dimensions is a concave function. So that implies the result above by taking delta n to be the first unprotected operator and the previous ones to be protected. Where for me, protected just means that their dimensions don't depend on marginal couplings. So they're constant over the conformal manifold. So this is actually a rather natural result, because if you just take linear combinations of operators, it's a general fact that the sum of the lowest n eigenvalues is concave for any n. And we already see this kind of thing in CFT as a function of spin. So the dimension of lowest lying operator of a given spin is known to be a concave function of spin. And we know that the same thing is true as a function of charge, at least asymptotically for large charge. So here, it's a similar statement, but over marginal couplings. So we're talking about a family of CFTs. So we're going to learn from this about conformal manifolds, their global properties, and also about unprotected operators, which is sort of normally difficult to learn about. But let me try and give a very fast argument why you should believe this statement. So let's consider a two-point function of this lightest scalar O, with dimension delta, on the sphere of radius r. I take log of this quantity, and I take two derivatives with respect to a marginal coupling g. Here I'm just focusing on a single marginal coupling, which couples to some marginal operator, but this argument can be applied with multiple marginal couplings. So the derivative brings down integrated marginal operators, and on the right-hand side I get second derivative of delta. On the left-hand side, I get this variance type quantity. And so specifically, this is the variance of the integral of L in O vacuum. So basically, it's just a kind of trivial consequence of unitarity that this should be positive. But that's, of course, too naive, because this is divergent. There's UV divergence when operators hit each other. So we need to find a finite positive quantity. So okay, we should regularize. And you can easily handle the singularities where the L's hit the O's just by cutting out balls, small balls around the poles where those operators are inserted. And then I still have a variance of some modified operator. I just change the integration range. But what's more difficult, and so that's still positive. But what's more difficult to handle is the singularity where the L's hit each other. But you can actually handle that by analytically continuing in the dimension of L. So as I take delta L away from D, away from marginality, and bring it back, I get something, you can actually show that you get something finite and positive, but it's not exactly what you started with. It's not exactly this second derivative. You can compute that there's a non-analytic piece living exactly at delta L equals D, given by a contact term, which provides this affine connection term. And that's exactly the term you need. They conspire together to give you something covariant, which is the covariant second derivative of the scaling dimension with respect to the marginal coupling. So in this way, you prove that, so you can do this with the Hessian matrix. So you add some indices. So you prove that the Hessian matrix is negative definite. So now let's test this. So the only example I know of in odd dimension where we really have access to unprotected data is this family of 3D n equals 2 theories with 3 chiral superfields and a cubic superpotential. It has strongly coupled fixed points, and the marginal coupling tau lives in CP1, mod by the discrete duality group S4. So a fundamental domain is one little triangle here. This theory was studied by Strassler a long time ago, and more recently by Baggio et al. And they used epsilon expansion and the bootstrap to get some approximations to low-lying unprotected scaling dimensions as functions of tau in this very nice paper. So here is their plot for the lightest flavor singlet dimension. And qualitatively, it looks like this is in tension with what I said, because this function has a minimum at tau equals 0, and its images under duality. But that's actually a singular orbifold point. It's a corner of the fundamental domain. And so that's sort of okay, something goes wrong there, but it needs to be that the second derivative is negative on either side. So the prediction is that it should be some kind of sharp cusp minimum. Right? The claim is that second derivatives are negative everywhere. So here I'm focusing on like some real slice. So let's test this. Well, here in black, I'm plotting their epsilon expansion, so exactly the same plot, now just along this real slice. They use data from d equals 4 minus epsilon. So I improved this epsilon expansion by also adding d equals 2 data and performing a two-sided pade. So those authors actually noted that something must be going wrong at tau equals 0 because this red dot is a bootstrap upper bound, which is not satisfied by their curve. So something's going wrong near that point. And indeed, including this extra data, I find this blue curve, which does go below the red dot, and has this expected singular behavior at tau equals 0. And I checked indeed that the covariant second derivative is negative everywhere along this real slice, as predicted. And you can actually see that the mechanism for this cusp is that there are additional marginal operators associated with symmetry enhancement at precisely that point, tau equals 0, and these lead to this singular behavior at that point. So we can also learn from this about the global structure of the conformal manifold. And while the usual law is that conformal manifolds of 3D CFTs should be compact, here I'm telling you that there's a whole bunch of concave functions, and actually smooth compact manifolds do not admit smooth convex or concave functions. So it must be that what happened on the previous slide is generic. Well, if this usual law is correct. So it must be that in odd space-time dimension, compact conformal manifolds must have singular points. So this is a sort of interesting, quite general conclusion coming from this result. So before wrapping up, let me give some outlook. So I'm also thinking about deriving similar results in even space-time dimension. And there it's a lot more complicated because marginal operators generically mix with the identity operator on the sphere. So things are just a lot more technically complicated. So in particular, it would be very interesting to understand the case of planar n equals 4, where something even more amazing happens. So there it's not just the lightest unprotected operator that's concave, but actually, as I showed you, all of them look concave as functions of lambda, all the single traces. So it's almost as if what's happening there is integrability says that each state is in its own superselection sector. It has its own quantum numbers. So it's sort of related to level crossing. You're able to apply this argument to all of them without without just landing on the lightest one. It would be interesting to explore the relation to CFT distance conjecture and also to get similar results in defect CFTs. So to summarize, in odd space-time dimension, the lowest scaling dimensions are concave functions over conformal manifolds, and compact conformal manifolds of odd dimensional CFTs must have singular points. And I tested these statements in 3D n equals 2 theories. Thank you.
Thanks a lot. Are there any questions? Yeah, Nadav.
Yeah, so you mentioned it, so maybe you don't want to talk about it. Defect conformal manifolds are quite ubiquitous, and there are many that are compact, but maybe they correspond to homogeneous spaces. So actually, all data is constant. So
Yeah, there are these examples where all the data is constant. So there, this is sort of trivially true. Yeah, do you have examples in mind where they're...
Yes.
Yeah, which examples? It has to be odd. I mean, for this to apply out the box, has to be...
It's line defects in ABJM.
Yeah, I think it would be really interesting to think about. But it should be like, I mean, for this argument to apply, it should be a local operator in the defect that defines the marginal coupling, that defines the marginal operator. So not a bulk operator. Yeah. Okay, well, maybe we can discuss.
Can I ask a question?
Sure.
Yeah, so in your argument, how does the dimension is odd play a role?
Yeah, so first thing is that in even space-time dimension, in general, there's a log divergence in the partition function on the sphere. And you can subtract this away, but it makes the finite piece ambiguous, which means that, I mean, that plays a role in this argument because that's how the two-point function is normalized. So you get extra contributions from like derivatives of the partition function. But these are now scheme-dependent ambiguous quantities. So you should assume a certain enough supersymmetry, actually, that this finite piece of partition function becomes well-defined. So in 4D and 2D, this is understood. So first, you need to assume a lot of supersymmetry. But second, you still have this confusing issue that marginal operators in even dimension are always violating my assumption that they're even integer gapped from the identity operator. And this means you can write down some counter terms where they mix on the sphere. So,
but do you expect the mixing can be absorbed by, like, here you add a connection term which absorbs some?
Yeah, I mean, it's not that I don't think this result can work in even dimension. I just think it's a lot more complicated. Okay. You know, here you need to pick some scheme and deal with divergences in a kind of reasonable way. And I think that can be done in even dimension as well. It's just a lot more complicated, and there are more contact terms you need to worry about.
In principle, it can work. Yeah, thank you.
Kolya, you had something?
So it's a more like technical question. So you kind of use both hard sphere regularization and also dimensional regularization, but dimensional regularization, like in particular, probably breaks conformal symmetry. Is it not a problem?
Well, yeah, I think you could probably do all of this with just dim reg. It's just that it's a lot simpler actually if you also cut out these balls. I think if you just did this kind of dim reg, it would also work. You're saying this, I mean, I'm just taking the integrals I have, and they depend on delta L, and then I'm just analytically continuing the value of delta L. So, yeah. Oh.
So could you remind what's wrong with applying this to ABGM and planar limit?
Well, the thing about planar limit, I mean, what's important here for making odd dimension simple is that the sphere partition function doesn't depend on marginal couplings. This you can show in general for a finite n, like for a genuine CFT in odd dimension, this is true. But in ABJM, you have dependence on n, which is discrete coupling, or discrete quantity. But dependence on n and k. But in large n limit, you now get dependence on their ratio, which you weren't supposed to have. I mean, that becomes marginal coupling, but so it kind of looks, in large n limit, it sort of behaves in this way more like an even dimensional CFT. In the sense that the partition function depends on this quantity which used to be discrete, but is now marginal coupling. Maybe it's an interesting halfway house between... Yeah.
Okay, maybe we should leave it here, but very interesting. Thank you very much.
Thank you. Sorry, I dropped it.
Yeah, so the next speaker is, I don't know how to pronounce.
Nairz.
Nairz. Thank you. He's going to speak about beyond the tensionless limit.
Okay, so hello everyone. First of all, of course, thank you to the organizers for giving me the opportunity to speak about a series of works under the umbrella term of going beyond the tensionless limit. So this was done in collaboration with my supervisor Matthias Gabadil, Rajesh Gopakumar, and 2 master students, Dennis Kempel and Felix Lichtner. So what I mean by going beyond the tensionless limit is the following. Our starting point is this very well controlled and essentially provable instance of the ADS-CFT duality. So when you take ADS3 times S3 times T4, which has mixed flux, you turn off all the R flux and you have minimal NS flux. It has been shown that this is the same as the 2D CFT symmetric product orbifold of T4. This manifests in a very pleasing way, but it is at a special point. For example, this tensionless string theory has a higher spin symmetry, and as soon as you turn on mixed flux, this can no longer be the case. It becomes quite difficult to study using worldsheet methods, but we know that it's the same as the CFT, and so this perturbation of turning on the RR flux is simply exactly marginal coupling. And so we can study this perturbed CFT using the more well understood framework of CFT perturbation theory. To understand the more general case and also maybe the CFT in its own right, as we heard in the morning, this might be of some interest. Okay, concretely what we want to do is understand how the algebra in this deformed theory looks. And so we look at right-moving supercharges here and S tilde and how they act on quarter BPS states in this theory. These are characterized by being annihilated in the free theory. As soon as you turn on the coupling, there can be transitions, and in particular, these have anomalous dimensions. And when we look at the BMN limit, we see that this supercharge action has an effective description by a dynamical spin chain. Furthermore, our framework sort of allows us to study the conceptual question of how these geometric ADS3 times S3 directions emerge from this 2D CFT. So this is what I will try to outline in the next few minutes, but to do it I have to introduce one of the best CFTs in the world, the symmetric product orbifold CFT. So when you take a CFT X, its symmetric product orbifold is obtained as follows. You take the CFT X n times, signified here by the lines, and then you mod out by the permutation group action. Concretely, what this means is that in this CFT there are local operators called twist operators which implement a permutation action. So if you put the sigma here at this point and you read this diagram from left to right, you see that it implements the 1, 2, 3 cycle. If you take X equal T4, this theory has a tower of BPS states, which I call ket W. They are half BPS states, and in fact they are themselves twist fields. So they have this non-trivial permutation structure. As far as the spectrum is concerned, these are the analog of trace set to the J in n equal 4 super Young Mills. And just as in n equal 4 super Young Mills, BMN is taking J to infinity, here the BMN limit is taking W to infinity. And there are similar results in that original paper already for the string theory side. Okay, these states are protected, so to have something more interesting, we have to go 1 less BPS, which are the quarter BPS states. And they are actually descendants of these half BPS states. Schematically, they look as follows. You pack on all the fields you want, as long as they are left moving. This is a quarter BPS state. And these fields, these alphas are bosons, psi's are fermions, and they have a mode number p. These p are quantized in 1 over w. That's the free theory. Now this theory is perturbed by an exactly marginal coupling called phi. This is a descendant, a supercharged descendant of sigma 2, where sigma 2 is, big surprise, a twist field. It's a sum of all transpositions, and it's depicted here in the top right. You can think of it as interchanging 2 colors. So when we have a quarter BPS state and we look at it in perturbation theory, what can happen at first order looks roughly like this. So you have this W state, and then you have 1 perturbation. If you imagine that these 2 legs eat these 2 legs, the last color is also permuted, and you transition to the W plus 1 sector. There's another planar diagram where these 2 legs eat adjacent legs, and it undoes a permutation on one of the legs, and you transition to the W minus 1 sector. So this perturbation theory actually already at first order has some sort of length changing effect. Okay, That's all we need to know. Now go back to the problem. We want to calculate how these supercharges act on quarter BPS states, and to be concrete and simple, I choose this quarter BPS state, which is just two bosons acting on the vacuum, the half BPS vacuum. To see how this S tilde can act on the state, you basically have to write down all the states it can transition to and calculate the transition elements. There's a quadrillion states, and it's but in this BMN limit there's a certain simplification, namely that the transitions to almost all of them are at least 1/W suppressed. And so if you want to look at how this supercharge acts, you can focus on the order 1 coefficients, and these are two states who are of a very simple form, namely S tilde takes one of the bosons, here the second one, turns it into a fermion. They can have a different mode number, so the Q's don't have to be the P's for now. And because of the length changing, this S tilde shifts the W up by 1. And these transition elements here, we can explicitly calculate in the perturbation theory. And I plot them on the next slide here. So this is this transition element as a function of Q1, which is the mode number of the boson. And what you see immediately is that they're all very small. And then they have extremely sharp peaks when Q1 gets close to one of the mode numbers of the initial of the bosons in the initial state. And so these points are spaced in 1/W. This is W300 or something. As you increase W, these peaks become narrower and narrower. And so effectively, as W goes to infinity, you want to describe this as follows, that S tilde eats the state, and it really, there's no sum over Q here anymore. It acts on the first alpha, turns it into a fermion with the same mode number P1, or it acts on the second alpha and turns it into a fermion, and it shifts the length by 1 upwards. And there's a coefficient here in front, which we calculate. So this is some sort of individual mode number conservation in this BMN limit. Okay, we can more effectively describe this, elegantly describe this by some commutator. So we prescribe the following commutator, that S tilde, the right moving supercharge, doesn't commute with the boson. Instead, it turns it into a fermion with some momentum dependent prefactor, and it inserts some Z plus, which we define by a length changing effect. Q tilde is the conjugate, and it acts as the conjugate. In particular, it lowers the length by 1. So to do this, we have to do some analytic continuation to get these coefficients, although we calculated them at finite W. This is sort of at infinite W. This prescription is consistent with the anomalous dimension and with the consistency of the algebra on shell. So this is exactly the same as in Nicholas's 2005 paper originally of this dynamic SU2/2 spin chain. Okay, if you give this prescription, you get a system which has an S matrix, and this S matrix satisfies the Young-Baxter equation. So it's integrable, and it was also found using worldsheet methods here. Also by self-consistency, you find an anomalous dimension for these magnons, which takes the square root form. In particular, the effect of the NS flux is that here is not a 1, but a p squared. And also this square root form was already found using semi-classical methods in these papers and others. All right, that's one part of the story. Another thing I want to talk about, so this is sort of infinite W. We can also look, since our method is calculating at finite W, we can look at large and finite W and study the following conceptual question. Namely, okay, obviously A is 3 times S 3 times T4 in light conjugate has 8 geometrical directions. And the symmetric product orbifold of T4 has 4. So, okay, you might say the T4 goes with the T4, but what happens to the other 4 directions? And how do they emerge from the CFT? At least at strong coupling, they should be somewhat visible. The qualitative answer is the following. So as I mentioned, at the free point, you have this higher spin symmetry and everything is completely degenerate. You don't see any difference. But when you turn on the perturbation, this singles out some eigenvectors, and we see some qualitative differences in this large W limit. So I plot them here in a certain sector. These are the eigenstates made out of 2 fermions. And almost all of them look like the orange ones. So we call them short. They have coefficients which are peaked at select values of the mode numbers. Then there's exactly one state which combines almost all of the mode numbers together, which is shown here in blue. And when you look at the anomalous dimension of these states, they actually behave exactly like you would expect the BMN magnon in the S3 direction to do. They evade sort of the off-shell algebra analysis from before because they combine all of the states together. On the other hand, the short states behave like a 2-magnon state of the T4 directions. So this is our interpretation that that we can see from the eigenstates, we can see these geometric directions emerge. Okay, just to conclude, I've shown you a bit about the calculation we did in the Orientifold in this BMN limit and how we saw that there is an off-shell symmetry algebra, a dynamical spin chain describing this supercharge action, that limit, some sort of integrable corner of this theory. And I've also quickly talked about the conceptual question of how you can see geometric directions of this ADS3 times S3 emerge from this 2D CFT, although there's a lot of open questions about this, which I would be interested to explore in the future. For example, since they're massive magnons, if they behave more analogously to ADS5 times S5 magnons. All right, thank you very much for your attention.
Questions?
Hi. So what about massless?
Yeah, so I would say, these ones are the massless ones. So also here, there's no m squared. So these are sort of the T4 magnons. They are made out of T4 orbifold fields. Also, sort of classically, the asymmetry generators of S3, which rotate the S3, they are SU2 affine algebra in the orbifold, and they are bilinears in the fields. So already there, they're not really independent. So these T4 magnons sort of form bilinears, which give you a single S3 direction. That's the qualitative way.
Other things? Someone at the back.
So am I understanding correctly that you're saying that S3 is actually more like a bound state of two fermion states?
Yes, I mean, I don't know exactly, so there's no sort of position space picture. I don't know in what sense it's a bound state, but yes, of course, yeah, intuitively I would also see it as a bound state of
I see.
I mean, also when you look at bound states of the S matrix, they sort of give the correct spectrum at least for what you would expect from massive directions.
Well, I guess perhaps you know, but like there is also something similar happening in GKP string.
I don't know, but maybe you can tell me later.
Well, I guess you can ask Benjamin.
Okay.
More things?
Questions? Arkady Zeitlin was raising his hand before.
Okay. Arkady?
So you started with saying something like you want to include Ramon flux, and then you considered some perturbation which you think is natural. So what's the evidence that that perturbation actually corresponds to inducing switching on Ramon flux on ADS3S3? So the evidence was like this BMN dispersion relation, or what's the evidence?
I mean, this is sort of an old matching of moduli. You have the moduli in the orbifold theory. 16 of them correspond to deforming the T4, and then there's 4 left which come from twisted sectors. You would imagine that your modulus has to come from the twisted sector to break this orbifold structure. And then there's a paper by Spentavadi and Justin David where they go through in more detail and analyze the charges and the symmetry, how these moduli transform under the global symmetries to propose this matching of the Ramon flux with this field. But yes, a posteriori, maybe also our dimensions are also an evidence for this.
What what about on string side? So you have your string description, then you can ask which operator corresponds to switching on Ramon for, right?
Yes.
And that you can do in NSR kind of for hybrid formalism in principle.
Yes.
So that should correspond to that deformation.
Right, it does. So you can do it using the DDF construction. There's DDF operators, you basically take the dual to this state, and then you apply the DDF operators. According to these, you also have to do some worldsheet supercharges, whatever. You integrate over both, both coordinates, and it exists. But it's not a calculational advantage, I would say.
Anything else? Okay, looks like there are more questions for now, so thank you again.
Before we leave, just an announcement for those going to the conference dinner. You can either travel yourself, or we will go as a group from here at 5 p.m. and at 5 p.m. Okay, the dinner is at 6, and please remember to bring your dinner tickets. Again, as we mentioned, they are inside the badge. Yeah.